Thanks, Alexander. Good morning, everybody. I am glad to welcome you to my lecture about the potential of ventilative cooling in German residential buildings. The content I will show you in the upcoming presentation has been mainly developed in a research project on behalf of Velux Germany. As you certainly know, the German energy-saving ordinance for buildings aims to ensure that buildings are very well insulated and constructed with a nearly tight building envelope. This is important for the winter period in order to minimize the heat losses. However, these requirements raise several new challenges, cooling in particular. As active cooling implies additional investment costs and an increase of the energy demand, the use of active cooling systems would comprise the initial target of high-performance buildings. In contrast to that, ventilative cooling is a very cost-effective cooling measure. However, it is currently not widely considered by building planners in the residential building sector. One of the reasons for lack of attention might be that the potential of night ventilation cannot be sufficiently estimated. To overcome this lack of information, we analyzed the potential of ventilative cooling into typical new-built residential buildings in Germany. One part of our study was focused on the critical parameters which lead to an overheating risk. In the second part, we determined the impact of increased night ventilation on the indoor climate and the theoretical cooling demand of residential buildings in Germany. In the study, we proceeded as follows. First, we chose two case studies, one for a newly built single-family house and one for a multi-family building. Requirement was that the buildings should be well known, for example, already used in scientific studies, and that should be representative for newly built residential buildings in Germany. Second, we analyzed different energy concepts by means of the monthly energy balancing method of DIN V18599. Third, we proved the summer heat protection with the simplified verification procedure of DIN 4108 Part 2. Then, finally, we assessed the summer indoor climate in critical rooms of the case study by means of a thermal building simulation. And last but not least, we developed a calculation model for implementing night ventilation in our thermal building simulation in order to analyze the potential of ventilative cooling. For the case study of the single-family house, we have chosen an archetype building of the database of the German Center for Sustainable Buildings. This archetype building was already used in diverse scientific studies. The floor plans are taken from a typical prefabricated home offered in the German market. This single-family home has a total living area of 152 square meters on ground floor and top floor. The ridge of the sloped roof is east-west orientated. On the southern facade, the building has large window areas and there is no roof overhang. For the case study of the multi-family building, we have chosen a real building which was erected in Munich within the scope of the German research initiative NF-Stadt. This building consists of 15 residential units on 5 floor levels, with an average unit size of about 70 square meters. All 3 flats of a story are north-south orientated. The entrance of the flats is in the north. The southern facade has large window areas, and the building has a flat roof with no roof overhanging. Due to the very short time, I cannot show the results of both case studies in detail. I decided to focus on the results of the multi-family building because on the one hand, because there are much more units in multi-family houses in Germany. On the other hand, due to the higher internal loads per square meter, the units in multi-family buildings stronger tend to overheating in Germany. To carry out further investigations, 3 energy concepts were assumed for different standards of thermal insulation. The reference case is a building concept according to the minimum requirements specified in the energy saving ordinance. In addition, one concept for a KfW Efficiency House 55 and another one for a KfW Efficiency House 40 are developed. The KfW Efficiency House levels are defined by the German Development Loan Corporation. They are used in the loan programs for energy efficient new building retrofitting. You can see the estimated heat transmission coefficients of the building elements, the solar heat gain coefficients of the window glazings in this line, the air change rates through leakages under 50 Pascal pressure. Estimated building services consists of an electric air-to-water heat pump used for heating and domestic hot water. The heating energy is transferred to the space through an underfloor heating system. Domestic hot water is prepared in a centralized storage and it is distributed to the taps with circulation. Multifamily building is ventilated by a mechanical ventilation system. In the reference case, an exhaust air system is considered. For the KfW efficiency houses, a balanced ventilation system with heat recovery is assumed. The systems are user-controlled with a year-round operation, which means no switch-off during summer periods. Second step, the critical rooms in respect of summer overheating are approved if they fulfill the minimum requirements for summer heat protection according to DIN 4108 Part 2. These requirements are temperature related in order to guarantee hygienic and comfortable indoor climate and to prevent structural damages. For the proof of the summer heat protection, there are two verification procedures. One is a simplified verification based on room characteristics like window area, solar heat gain coefficient, reduction ratio of solar shading system, and net floor area. Another way to do the verification is thermal building simulation under given boundary conditions. In our study, we only used the simplified verification process. The thermal building simulation we have performed within our study was not in accordance with the requirements of the standard DIN 4108 Part 2. On this slide, you can see the results of the simplified verification procedure for the multifamily building. In this building, we identified 6 critical rooms, which are living room and sleeping room of flat brown and green marked, kitchen and living room in flat 2, red and purple marked, and child room 2 and sleeping room of flat 3, blue and yellow marked. By putting a heavyweight construction and shutters as solar shading systems, 5 of the 6 rooms fulfill the verification without any additional measure. Only the kitchen of flat 2 increased night ventilation with an air exchange rate of 2 times per hour is needed to meet the requirements. If we would have chosen a lightweight construction or no shading device, the verification procedure would have been not fulfilled without increased ventilation. In order to have a closer look at the critical parameters of the overheating risk, for each case study a thermal building simulation was conducted. The software we have used is Transit 17. We did a whole building simulation of the single family house. The simulation model of the multi-family building comprised the top floor, which is the story with the highest solar radiation impact. The simulation time step was set to 1 hour. The parameterization of the simulation model was done where reasonable in accordance with DIN 18599, and the simulation models were calibrated with the results of a monthly energy balance. For verification, air exchange between the different rooms was not considered in the case of night ventilation. As I mentioned before, except in the case of night ventilation. As I mentioned before, the chosen approach is not in compliance with the verification process of summer heat protection according to DIN 4108 Part 2. Chosen parameters in conformity to the default values of DIN 18599 are the internal heat loads, domestic hot water demand, and the set point temperature for cooling and heating. The input load of the single-family house is set to 45 watt-hours per square meter and day, and in the multi-family building to 90. In contrast to that, DIN 4108 Part 2 provides 100 watt-hours per square meter and day, independent from kind of building and in all rooms. Use the German reference climate, which is equal to the test reference year of Potsdam. The calculation of infiltration and ventilation, except night ventilation, was based on constant values without hourly variation. For modeling the surroundings, it is assumed that there is no shading due to adjacent buildings, trees, or due to the topology. In addition, it is assumed that the buildings are surrounded by dispersed suburban developments, which corresponds to a medium windshield class. The reflectance of the ambient surfaces is set to 20%. User profiles, as you can see on this slide, were developed on the basis of the daily internal heat loads according to DIN V 18599 Part 10. The division into hourly values was carried out in accordance to DIN EN ISO 13791, which distinguishes between room types, kitchen, dining room, bedroom, and bathroom. As said before, by means of the thermal building simulation, we analyzed the influence of different parameters on the overheating risk of residential buildings. For this purpose, the following variations of the building concepts were made. First, variation of the insulation level, as I explained some slides before. Second, variation of the building construction between heavyweight construction with concrete ceilings and masonry walls, and lightweight construction with suspended ceilings and wooden walls. Third, variation of the window size between a standard sized window and an increase of the window area by 15%. And fourth, a variation of the control of the solar shading systems. Analyzed control strategies comprise an automated control with solar sensors. The second variant is a time control strategy based on time schedule and weather forecast. This represents the situation if the user is not at home over the course of the day. The solar shading system is activated in the morning if an outdoor temperature of above 30 degrees is forecasted. The system is reopened in the evening at 7 p.m. when the user comes back home. The third control strategy is a user control based on the internal temperature and the solar radiation supply. The user activates the solar shading devices as soon as the indoor air temperature exceeds 26 degrees, while the total radiation incident on the facade exceeds 300 watt per square meter. On this slide, you can see the excess temperature degree hours in the critical rooms of the multifamily building for 3 thermal insulation levels. The temperature degree hours are calculated from the difference between the hourly operative temperature and the reference value of 26 degrees, cumulated across all hours with excess temperature. The dark blue columns represent the reference case. The purple columns show the results of the KfW efficiency house 55, and the bright blue columns stand for the results of the KfW efficiency house 40. The red line represents the maximum admissible threshold value of 1200 Kelvin hours according to DIN 4108 Part 2. Can be noted that results proved my original thesis that highly insulated buildings with airtight envelopes tend to summer overheating. Most critical are kitchen and living room. That shows the excess temperature degree hours for different solar shading control strategies. Again, dark blue represents the reference case with an automated control. The red columns are the results of the user control strategy and the green columns of the time control. The purple columns show the results of a variant without solar shading system. It can be seen that a solar shading system is urgently needed to avoid overheating. The different control strategies showed also great impact on the overheating risk, Especially the time control strategy leads to excess temperatures in several rooms. The last result graph shows the influence of the building design on the overheating risk. The dark blue columns again represent the reference case with a heavyweight construction and normally dimensioned windows. The orange columns show the results of a lightweight construction, and the bright blue columns stand for an increased window area by 15%. The lightweight construction leads to an increase of the overheating risk. A bigger area, however, is not a great problem as long as an adequate shading system is used. Next step, the building models were adopted and a calculation model for considering ventilative cooling was implemented in the TRANSIS model. The effects of natural night ventilation are modeled using the air mass flow balance method. This means that the air mass flow rate, which is conveyed into a zone, will leave the zone in the same time step, so the occurrence of low pressure or overpressure is prevented. Air mass flows which enter the individual rooms through the window openings are calculated following Annex 1 of DIN EN ISO 13791. Both wind and thermal buoyancy induced by a temperature gradient between the interior and the exterior are considered as driving forces. For reasons of simplification, DIN EN ISO 13791 assumes that there is no superimposition of these two driving forces. Instead, the stronger force during the respective time step is considered. Increased night ventilation occurs only by natural ventilation. No additional fans are considered. All openable windows serve as ventilation openings, depending on the accessibility from the outside and the use of the room. Different effective ventilation cross-sections are estimated. In the bins, the windows are assumed to be tilted and the doors closed. Windows which are accessible from the outside are assumed to be tilted. All other windows are considered to be half open. The effective ventilation cross-sections of the windows are calculated using the height and the width of the openings. Windows with a fixed glass parapet are assumed to have an opening height of 2/3 of the full window height. The effective cross-section of a tilted window is calculated with a tilt gap of 11 centimeters. The influence of a closed shutter on effective cross-section is estimated with a reduction factor of 30%. The night ventilation is implemented with a time-dependent user control based on the external and internal temperatures. If the internal temperature is above 24 degrees, while the external temperature is below 22 degrees, the windows are opened in the period between 11 p.m. and 7 a.m. The windows remain open until the internal temperature falls below 18 degrees or rainfall occurs. You can see the airflow model, which is used for simulating ventilative cooling in the multifamily house. For reasons of simplification, the story has been divided into 7 ventilation zones. Ventilation zone 1 to 6 have openings on opposing facades. Ventilation zone 7 can only be ventilated through one window. Shows the impact of night ventilation in the living room of the single-family home in the night of 20 to 21st July. The profile of the outdoor temperature is marked as a yellow line, and the indoor temperature as a light blue line. The blue curve represents the wind velocity. The air wall flows induced by night ventilation are represented as columns. In hours before night ventilation sets in, the indoor air temperature remains relatively constant above 24 degrees. The outdoor temperature drops from 13 degrees at 8 p.m. to 18 degrees at 5 a.m. Sunrise, it rises above to 20 degrees. Night ventilation starts as soon as the outer temperature falls below 22 degrees. Night ventilation remains active until 7 a.m. in the morning. In the first hour, the force driving the air exchange is wind on the east facade. In the next 2 hours, thermal buoyancy is the driving force. After 4 a.m., the wind velocity augments notably, and the wind on the south facade becomes the driving force. After 6 o'clock, the wind changes to eastern direction. As expected, the indoor temperature continually declines to 20 degrees after night ventilation has begun. In the morning hours, when the wind on the east facade passes through the kitchen into the living room, the indoor temperature rises again until it recovers 23 degrees at 8 a.m. The reason for this development becomes evident from the next figure. Here, the profile of the outer temperature, red line, and the indoor air temperature in the living room, the light blue line, are illustrated. Additionally, the surface temperature of the enclosing building components, floor, ceiling, and external walls are presented. The figure shows that the air temperature starts at a higher temperature level, but night ventilation reduces it much faster than the temperatures of the enclosing surfaces. This effect is due to the higher heat storage capacity of the building components compared to that of the indoor air. At the moment when the airflow passes through the kitchen into the living room and no longer directly from the outside, the temperature difference of the air mass flow is no longer sufficient to discharge the heat dissipated by the building components. In consequence, the indoor air temperature is reheated until a balance between the air temperature and the surface temperature of the building components is achieved. At the end of night ventilation, parts of the storage masses has been discharged again. This can be seen in a reduced surface temperature of 1.5 Kelvin compared to the evening hours. In this figure, you can see that night ventilation reduces the internal temperature in the multifamily building in mid of July almost by 3 Kelvin, from 28 degrees without night ventilation down to 25 degrees with night ventilation. Besides, night ventilation can also ensure that the operative temperature continuously remains below 26 degrees across the entire summer cooling period. As shown before, the parametric study on the multifamily building identified problems associated with excess temperatures, especially for the lightweight construction and the variant without solar shading. As can be seen in this figure, these temperature problems can be almost entirely eliminated in both cases by using night ventilation. The remaining excess temperature degree hours in the kitchen of flat 2 are far below the threshold value of 1200 Kelvin hours. I want to close my lecture with a short summary. Summer overheating problems are no big issues in typical newly built residential buildings in Germany. Most critical is the intelligent use of solar shading systems and the heat storage capacity of the building components. Ventilation has been proved to be an efficient and effective measure to minimize the risk of overheating. It can make the use of an active cooling system dispensable. Even for the worst combination of the parameters, which are the use of solar shading system and the heat storage capacity of building components, night ventilation can guarantee comfortable interior temperatures in Germany. With this statement, I want to close my lecture, and I want to thank you for your interest.